Hi, my name is Sheel, and I'm a graduate student with the PyStar Lab in the Department of Computer Science and Engineering at Texas A&M University. In this talk, I'll be presenting our work titled A Joint Imitation Reinforcement Learning Framework for Reduced Baseline Regret, or JIRL for short at IROS-2021. This is a joint work with Sumedh Pendurkar, my advisor Guni Sharon, and Josiah Hanna. In many real-world applications, there are inefficient controllers currently in use that can be optimized. At the same time, it is necessary to maintain a baseline level of performance while doing so. One example is the traffic signal domain. We all have first-hand experience with inefficient signal actuation. While such controllers can and should be optimized, performance degradation, even if temporal, are not acceptable, as this can jam an entire city. Similar issues also arise in tasks involving industrial robots, mobile robots, and healthcare assistants, just to name a few. Reinforcement learning, or RL for short, has been shown to outperform such suboptimal controllers. However, with RL, there's a very high chance that the learning agent initially performs worse than the existing controller. We formulate the problem as a standard Markov decision process. Our task is to train an optimized policy denoted pi theta that maximizes the expected sum of discounted rewards in a trajectory using online learning. At the same time, we desire to maintain a baseline level of performance during learning. The baseline performance is defined by rolling out a suboptimal baseline policy denoted pi b. Our goal is also represented by the blue line in the plot. It shows the performance of the policy being executed in the environment. Notice that the performance never goes below the baseline and improves eventually. Just a quick note, throughout this presentation, I may use the words policy and controller interchangeably. Broadly, there are two categories of approaches by which a policy may be learned, offline and online. Imitation learning, or IL for short, is an offline learning algorithm by which a policy is learned by optimizing on a collected dataset. Hence, there is no risk of unsafe exploration. However, the performance of the learned policy is limited by the baseline performance. In online learning, such as RL, exploratory actions are executed in the environment that might be unsafe. This results in poor performance in the early stages of training. A typical learning curve for RL is shown by the green line in the plot. However, eventually it is possible for the RL agent to outperform the baseline. Note that we do not assume access to a model of the environment. In our proposed JIRL, we aim to combine the best of both worlds, as can be seen by the blue line in the plot. Our objective is to avoid unsafe exploration and converge on the optimal policy. I'll go over the details of how we achieve this in the slides that follow, but first, I would like to show you a demo comparing JIRL with the state-of-the-art RL algorithm, soft actor critic, or SAC for short, on a few tasks.
In all our experiments on continuous control tasks, we mark an episode as a failure if the behavior policy performance is below a desired level. We demonstrate that JIRL can effectively learn from and optimize over a baseline demonstrator, resulting in fewer failures as compared to SAC. In the inverted pendulum task, the baseline policy manages to complete the task while performing suboptimally, as can be observed in the early episodes using JIRL. Eventually, both SAC and JIRL learn the optimal policy. However, JIRL encounters 9 times fewer failures as compared to SAC. In the lunar lander task, the baseline policy can land the probe but doesn't follow the optimal policy. It can be seen that learning from SAC leads to multiple crashes at the beginning. JIRL, on the contrary, leads to 44 times fewer failures. On the other hand, it takes slightly longer for JIRL to learn an optimized policy compared to SAC. In the Walker 2D task, the baseline policy can make the robot walk. However, it is possible for the robot to learn to run, as demonstrated by the performance of the final policy. Similar to SAC, JIRL trains the robot to run while reducing the number of failures by a factor of 3 as compared to SAC. In the lane following task, during the early stages of learning using SAC, The car goes out of the lane multiple times. This behavior is not seen in JIRL, as the baseline policy helps the car stay inside the lane. We use the same strategy on an RC car based on NVIDIA's Jetson Nano. We demonstrate that JIRL can successfully learn a policy that achieves a higher speed as compared to a baseline policy. After 45 minutes of training, the policy learned using JIRL completes a lap in 9.4 seconds, which is a 30% improvement over the baseline policy. The policy learned using JIRL is also smoother due to the feedback from the baseline policy during training. Note that for both SAC and JIRL, we use a simple reward function that incentivizes moving fast. SAC can achieve a smoother policy, but it comes at a cost of tedious reward shaping.
Next, I would like to formally define the quantity regret. Regret is the difference in the expected sum of rewards under the optimal policy and the expected sum of rewards under the behavior policy for a full trajectory. The total regret is shown by the shaded region in the plot on the right. We define the baseline regret as the expected sum of the positive difference in rewards under the baseline policy and the behavior policy for a full trajectory. The total baseline regret is shown by the shaded region in the plot. Existing approaches on baseline regret minimization usually make a few assumptions. Some assume access to a stochastic baseline policy for performing exploration. However, depending on the task, this might not be possible. In many domains, the baseline controller could be deterministic or rule-based, such as traffic signal controllers. JIRL, on the other hand, can be used with any type of baseline policy. Few other approaches define hard constraints to avoid regret. This approach, however, requires manually defining constraints beforehand. In JIRL, the agent rather uses heuristic constraints with the help of the baseline policy. Some approaches employ on-policy RL algorithms based on trust regions such as TRPO and PPO, which approximate monotonic improvement. JIRL, on the other hand, uses off-policy learning since the behavior policy and the policy being learned can be different. Initializing TRPO or PPO with a baseline policy is a suitable candidate for comparison against JIRL in terms of the baseline regret. The assumptions we make in JIRL are: number one, access to a baseline controller, for example, a suboptimal controller. Number two, using an off-policy algorithm. This is necessary since we leverage demonstrations from the baseline controller. Now let me walk you through a running example of our JIRL framework. At each time step, the baseline policy is assumed to provide a suggested action, AB, that is derived from its own internal policy. The RL agent determines if it should follow its own stochastic policy, pi theta, at the current state or defer to the baseline action. The agent consults the is-RL trustworthy module to make a decision on the action selection. Let's assume that in the first step, the is-RL trustworthy module decides to follow the RL policy. So ARL is sampled from pi theta and applied to the environment. The transition is then used to train the RL agent. In the next step, once again, the RL agent has to make a choice between following the baseline action or pi theta. Once again, the agent consults the is-RL trustworthy module to make a decision on the action selection. Let's assume that in the second step, the is-RL trustworthy module decides to follow the baseline action. So AB is applied to the environment. At the same time, ARL is sampled from pi theta, and AB and ARL are passed to the fabricate transition module to generate a fabricated counterfactual transition. The RL agent is trained on both the actual transition and the fabricated transition. I will discuss this motivation behind this in the next few slides. The RL agent uses the is trustworthy module through which it determines whether to act and explore or follow the baseline action and train towards imitating the baseline policy. The intuition is that when the RL agent is uncertain about its actions, it should be trained towards imitating the baseline policy. As the RL agent becomes more certain regarding its actions, it is allowed to drift further away from the baseline policy and explore other promising actions. We measure the level of uncertainty of the policy using entropy. Most continuous actions tasks use a Gaussian distribution to define the stochastic RL policy. The plot on the left shows the entropy for two different Gaussian distributions. As can be seen, the distribution with a shorter tail has lower uncertainty and has a lower entropy. The plot on the middle shows the norm distance between the mean RL action and the baseline action. We define a divergence value denoted rho as the summation of the RL policy entropy term with the norm distance. We factor in the divergence values over several time steps, denoted K, as we observe that small divergences can accumulate over time and result in a significant divergence. We observed this phenomena when applying JIRL to an autonomous driving domain, where the RL policy can slowly yet steadily steer the vehicle off the road. If the product of the probability of baseline action under pi theta is greater than the product of the divergences times the scaling factor C over k steps, the is RL trustworthy module decides to execute the RL action in the environment. The motivation behind adding a fabricated transition is that an RL agent aiming to maximize return will update its policy to shift probability towards AB from ARL, that is, towards imitating the baseline and reducing future baseline regret. The reward for the fabricated transition is penalized and set to be lower than the reward affiliated with the baseline policy action. Setting a constant penalty generally works for discrete action spaces, but might cause convergence failures in continuous action spaces. So to address this issue, we present a continuous penalized reward function that is inspired from a Gaussian distribution. In this case, the penalized reward tends to 0 as ARL gets close to AB. The fabricated transitions may bias learning away from the optimal policy. As a result, conversion to the optimal policy is possible provided only RL-induced transitions are considered eventually. As the training progresses, the accumulated safe divergence value is expected to decrease since the RL policy entropy usually increases. Consequently, RL control becomes more common and baseline and fabricated transitions are encountered less. If the underlying RL algorithm uses a bounded replay buffer, JIRL can learn the optimal policy. The plots here show the learning curves for different domains. The x-axis represents the number of time steps, the left y-axis the average reward per step, and the right y-axis the percentage of RL control. Vanilla SAC is denoted in green. JIRL that uses SAC as the underlying algorithm in blue, TRPO in orange, PPO in black, and the percentage of RL control in red. We perform post-training till the point where the RL agent starts getting similar rewards in both JIRL and SAC. In all four domains, JIRL resulted in a final policy that is at or above the vanilla SAC algorithm. Notice that the red line increases to 100%, representing the RL control shift in JIRL. Moreover, JIRL is shown to clearly reduce the baseline regret over vanilla SAC. The baseline performance can be seen on the left side of the JIRL curve, where RL control is at a minimum. In all but the lane following Carla domain, JIRL resulted in a final policy that is superior to the baseline policy. The discrepancy in this domain is due to the use of a highly optimized baseline policy, which SAC was unable to outperform. When adjusting the reward function to reward greater speeds, it is possible to surpass the baseline performance as demonstrated in the lane following jet racer domain. Next, we compare JIRL with TRPO and PPO, initialized with the baseline policy with respect to reducing the baseline regret. In all the plots, the better performing among TRPO or PPO are presented, but not both. We can see that PPO and TRPO present a fairly monotonic improvement in average performance, but with high performance variance, which leads to high baseline regret. Also, due to low baseline policy coverage, PPO and TRPO might suffer from initial degradation in performance, as seen in the inverted pendulum and Walker 2D domains. Unlike JIRL, PPO and TRPO were not able to reach the baseline performance in the lane following domain. Hence, these results are omitted for this domain. Empirically, we observed that JIRL reduces the accumulated baseline regret over PPO and TRPO by a factor of 10 in the inverted pendulum domain, 21 in the lunar lander domain, and 2 in the Walker 2D domain. To conclude, JIRL is shown to perform on par with the baseline during the learning process and eventually surpass a suboptimal baseline in all examined domains. Moreover, JIRL was shown to converge to a policy of similar quality as a state-of-the-art RL algorithm while reducing the accumulated baseline regret. JIRL is also easy to implement and can be added on top of existing state-of-the-art off-policy RL algorithms. Thank you for tuning in into this presentation. If you have questions or comments, please feel free to get in touch.